All right then, let's actually look at a new example that would be from this course specifically. Let's let G be any cyclic group. Okay, let me be nice. Let's call it H instead, because it's going to be the codomain. So H is generated by an element. Let's call it angle brackets G. As a good reminder, that means it's this element, this group looks like all powers of G, as n runs through all integers. Well, you can define an exponential map from the integers to H. X said G. What do we do with the integer n? We send it to G to the n. So that's why I'm using this notation, because it's exponentiation base G. And you can check for any two integers n and m that if you exponentiate n plus m, remember z is a group under addition, you get G to the n plus m. By properties of exponents, that's G to the n times G to the m. But that's the definition of our homomorphism applied to n times our homomorphism applied to m. So here, it's worth pointing out, this plus was the group operation in our domain. This times is the group operation in our codomain. So we do in fact see that we have a group homomorphism. What is the kernel of this map? Well, it's all elements in the domain being the set of integers, such that the function maps that element to the identity. Remember, again, it's all G in the domain, where phi of G is the identity. In this case, our G is actually an integer, so let's use integer notation instead. Our function takes n and sends it to G to the n, and so this is our set. Now we remember properties of cyclic groups. If you let D be the order of G, then there's this theorem that G to the n is equal to E if and only if D divides n. It's in the book, of course, they use K here, and n is the order of G, but I'm changing variable names, but that doesn't change the truth of the theorem. Although, I guess I could have rewritten this to avoid that problem. The point is, the elements in here all have to be multiples of D. So this set is D times Z. That is our kernel in this case. So, for example, if I let H be the cyclic subgroup generated by I, the non-zero complex numbers under multiplication, it has order 4. So then the kernel of this exponentiation map base I is 4z, corresponding exactly to the fact that I to the 4th is the identity, as is I to the 8th, as is I to the 12th, as is I to the negative 4th, and so on. On the other hand, if I try a new different H to be the group generated by two non-zero complex numbers, here, of course, I'll run into a problem. It's infinite order. So, the only way to get the identity is when n is 0. And finally, as one last pain in the neck example, if you take the trivial subgroup, well then 1 to the n is equal to 1 for all integers. So then the kernel of this one is all of z. Looking ahead, we will discover in a few weeks that knowing these facts about these kernels is actually going to tell us a shorter proof that this cyclic group is isomorphic to z mod nz. That's much shorter than the more complicated proof I had to give before.